Welcome to Structural Analysis 2. Today, we dive into the fundamental behavior and mechanics of arches. Unlike standard beams, arches utilize unique curved configurations to efficiently manage large gravity loads. In this module, we will explore the engineering definition of an arch, look closely at its anatomical properties, and break down how it dramatically reduces internal bending stresses. We will also examine how these classic structures are classified by both their physical geometry and their static determinacy. Let's begin by looking at the core structural actions that make arches so efficient. So what defines an arch? It is a curved structural member with an upward convex profile, supported at its ends to prevent outward spreading under gravity loads. The defining characteristic is horizontal thrust. Even under purely vertical loading, the supports must develop inward horizontal reactions, denoted as H. This horizontal action creates an internal hogging moment, mathematically expressed as H times Y. This hogging moment actively counteracts the standard sagging moment caused by vertical downward loads. By suppressing tensile bending, arches allow materials like masonry, concrete, and cast iron to perform at their highest capacities in pure axial compression. To analyze an arch, we must first master its anatomy. The springing line is the theoretical horizontal line, connecting the points where the arch rib meets its supporting abutments. The highest point of the arch profile is the crown, which often houses an internal hinge. The rise, H, is the vertical distance measured from the springing line up to the center line of the crown, while the span, L, is the total horizontal distance between the support contacts. Finally, the inner underneath curved surface is called the intrados, or soffit, while the outer upper surface is known as the extrados. The core structural mechanic of an arch is its ability to radically suppress internal bending moments compared to equivalent beam systems. Let's look at a simple span, L with a rise, H carrying a central point load, P. A standard beam experiences a maximum midspan bending moment equal to PL over 4. However, an arch evaluates its internal bending moment as the beam moment minus the horizontal thrust times the vertical rise, H times H. For standard parabolic profiles, this net calculation reduces peak design bending moments by up to 2/3, creating highly efficient and remarkably slender structural members. Arches are widely classified by their geometric shapes, which directly dictate their structural response. Parabolic arches are derived from quadratic curves. They are exceptionally efficient under uniformly distributed gravity loads, where they experience zero internal bending moment and operate in pure compression. Circular or segmental arches are formed by a single continuous radius. These were highly popular in historical architecture due to their standardized fabrication geometry and straightforward framework molds. Finally, pointed or Gothic arches feature two intersecting circular curves. This geometry shifts the internal thrust vectors closer to the vertical plane, minimizing the need for massive lateral abutments. Beyond shape, arches are classified by their static determinacy and support conditions. A three-hinged arch has 4 reaction components. Because it contains an internal hinge at the crown, it is statically determinate, making it completely immune to internal stresses caused by thermal changes or minor support settlement. A two-hinged arch also has 4 reaction components, but lacks a crown hinge, making it indeterminate to the first degree and moderately sensitive to settlements. Lastly, a fixed arch features rigid encastre supports providing 6 reaction components. It is indeterminate to the 3rd degree and highly sensitive to support movements, demanding completely unyielding abutments. Let's look closer at the determinate 3-hinged arch. This structure features 2 pinned hinges at the base supports, labeled A and B, and a 3rd internal hinge located at the crown, labeled C. This layout produces a total of 4 unknown support reaction components, 2 vertical forces and 2 horizontal forces. While standard static equilibrium provides 3 equations, the internal crown hinge provides the vital 4th conditional equation. The bending moment at C must equal 0. By isolating either the left or the right half of the arch and summing moments about hinge C, we can easily compute the horizontal thrust, H. The two-hinged arch removes the internal crown hinge, maintaining pinned connections only at supports A and B. This creates a more rigid structure that is indeterminate to the 1st degree. To solve for the redundant horizontal thrust, H, we apply energy methods like Castigliano's theorem of least work, dividing the integrated virtual bending work along the arch profile. Because it lacks a crown hinge to accommodate expansion, temperature changes induce secondary thrust forces. A temperature rise, delta T, produces an additional horizontal thrust, HT, calculated using the thermal expansion coefficient alpha, span L, and the arch's flexural rigidity profile. To finish our analysis, let's examine the mathematical geometry of these profiles. For a symmetrical parabolic arch with its origin at the left support hinge, the vertical height y at any position x is given by 4h over L squared times x times L minus x. Differentiating this gives the slope, tangent theta, at any section. Conversely, A circular arch conforms to a constant radius, r, relative to an imaginary center of curvature below. The radius r is calculated from the span and rise. Measuring x horizontally from the central crown, the vertical coordinate y is computed as the square root of r squared minus x squared, minus the quantity r minus h. In conclusion, arches are incredibly efficient structures because they convert high bending stresses into manageable axial compression. By generating horizontal thrust at the supports, they create a permanent internal hogging moment that counterbalances vertical gravity loads, reducing peak bending moments by up to 2/3. Thank you for watching this module on structural arches.